Hello everyone. Let's continue our discussion on the flow. So the next step after the optimized placement stage is to do a timing analysis with ideal clocks. The reason to do is to get an idea of how does the timing looks like at this stage. Because if there are any discrepancies or any accidental wrong placement done by the user or done by anyone else or done by the tool, that can be estimated right away over here, and we can do some fixes. Because if we identify those problems at the later stage of your physical design flow, that might lead to problem, and you might not even revert back to make those changes. Okay, so it's a very good idea to do a timing analysis at the placement stage itself with ideal clocks, assuming that there are no clocks, or basically assuming there are clocks but it's not routed yet. Assuming the clock the latency or the time required for the clock to reach from this port to this port, or to this port to this port, it's zero. So assuming that, we'll do a timing analysis only on the data path. Okay, so the timing analysis looks something like this. Your combinational delay is the flip-flop 1 clock to queue delay plus the estimated wire delay plus the delay of this particular cell plus the plus the estimate wire delay of between 1 and 2 plus the delay of 2 plus the wire estimate delay between 2 and flip-flop 2. So this will be your combinational delay. Similarly, for this section, the combinational delay will be the clock to queue flip-flop 1 plus the delay of 1, since there is no wires and there is an abutment over here. Still, there will be a minimal RC wire, but that's very negligible. So it will be the delay between flip-flop 1 clock to queue, the delay of 1 and delay of 2. So this will be the value of the combinational delay. This combinational delay has to meet certain criteria under the setup timing analysis with ideal clocks, and the criteria is it has to be less than the time period minus setup time minus setup uncertainty. So details of this setup timing analysis with ideal clocks is being done in the detail section of this course, but not over here, because we are giving an overview of the physical design flow. So we will be doing a detailed analysis of how did we arrive actually to this particular equation. We'll be doing all those in the upcoming videos in the next sections. In this section, we are giving you just an overview. So this particular combinational delay, we make sure that at placement stage or at optimized placement stage, we are actually meeting this condition, or if we are not meeting this condition, we are violating this condition by a marginal number, not by a huge number. Okay, so for example, your combinational delay is expected to be less than the time period, which is 1 nanosecond, the clock period, which is 1 nanosecond, minus the setup time 0.01 nanosecond, or 10 picosecond, minus the setup uncertainty, which is 0.09 nanoseconds or 90 picoseconds. So in the detailed video, we will be explaining why do we need this setup time, why do we need this uncertainty. So basically these uncertainties because of jitter, there are clock jitters, and this setup time is basically the internal flop delay. So we'll be talking about all those things in the upcoming sections. In general, the combinational delay should be less than 900 picoseconds, and that's expected. If it is not, if should be violating it, if let's say combinational delay is not 900 picoseconds but 1 ns, still it's okay, it's violating by 100 picosecond. Okay, so that's what we expect in that range, and not to a very huge number. So after we have done with the timing analysis, we get an idea or overview of how does the timing looks like, and we try to maintain the same around the same timing in the further steps as well. So further steps will include some more changes in the circuitry. Let's look into them. But before that, other than the timing and other than the setup timing analysis, we also do a data slew check. Data slew check basically specifies the data transition check, the transition number, or the what is the signal transition at the input and output of any of this logic. So whatever transition you see over here and whatever transition you see at the output are those within minimal range, and we come up with some range. In this case, we have taken a range of 20 picoseconds to 400 picoseconds. There are advantages and disadvantages of having a very low transition and a very high transition. That's why the data transition is expected to be certain limit. If the data transition goes below 20 picosecond, there is a problem that within a very short period of time there is a huge current demand, and that might lead to power overshoot. And if the data transition goes beyond 400 picosecond, there is a huge amount of time during this transition time. There is a huge amount of time period where your both NMOS and PMOS are on. that will lead to huge short circuit current. So this all will be we will talk about all this in detail in the upcoming sections, or in the detailed section where in the same course. Currently we look into we check across the complete circuitry, across the estimated wires, and check for the transition for this between these wires, and those transitions should be within certain limits. And we do this for complete circuitry. We check the transition from D in 2 to flip flop 1 or 1 on, and so on. We do it for all the data parts. Okay, and that's a very important check, because this still gives us an idea that whether a cell is properly located or not. For example, if this particular cell was accidentally placed somewhere over here, you would have seen a huge transition, because there is no direct connection possible from this point to this point. And the reason is we have this big block sitting over here. So we should be buffering, we should be routing from this point till this point with the help of some repeaters. And whether that is being done or not, that can be checked with the help of data slew check or data transition check. Okay, so that was the data transition check. After we have done with the basic timing analysis with ideal clocks on the optimized placement stage, the next step is to do a clock tree synthesis. So now we are entering into the clock world. So the clock tree, by clock tree synthesis, we mean that this clock 1, or for example this clock 1 should be reaching its respective flops. For example, this clock 1 has got its connection to flip flop 1, flip flop 2, flip flop the yellow color flip flop 1, and there is one more flip flop too. So basically this clock has to reach each and every flop at the respective time. That is one thing. And there is second thing, that the skew, there is a concept of skew where we expect the clock to reach at this flip flop and this flip flop at the same time. That is the expectation. So we have a detailed lecture on clock tree synthesis in a separate section. There's a detailed course on clock tree synthesis. You might want to have a look into that course, but let me give you a brief overview of the clock tree synthesis. So for example, let's take one clock. This particular clock 1 is expected to reach to flip flop 1, flip flop 2, flip flop 1 and flip flop 2 at the same time. That's basically the skew. If it is not flip flop 1 and flip flop 2, at least the flip flop 1, flip flop 2 which is sitting over here, it is expected to reach at the same time. And the reason is, if it doesn't comes at the same time, there will be a skew, and that skew might lead to timing violations. All this has been explained in a very detailed manner in a separate clock tree synthesis video. You might want to have a look into that, but this is the concept. Okay, and no, not in the clock tree synthesis, not only we just route this particular thing in a different fashion, but we also buffer them. And the reason is, with the difference between the clock routes with and without buffering. For example, this was the case without buffering. In this case, you see the wire length is very huge, so the number of resistance and capacitances that this clock port has to charge, that becomes very huge, and as a result of that you see huge transitions. So we need repeaters. As we said, that any person who's sitting over here, if he sends a signal, if he sends a shout, that shout has to reach the clock pin of the flip-flop 2 without any deterioration. So to maintain the originality of the signal, we add some repeaters in the path. So if you see, this particular signal now gets reconstructed with this particular buffer, and it is sent again. It gets reconstructed again with this buffer, it is sent again, and finally it reaches the flop. And similarly for the other clock 2 also. For the clock 2, it sends a signal, this buffer reconditions it or reconstructs it, it sends it again to this buffer again reconstructs it, and it is sent again, and then it is sent to its respective flops. So all this has been talked about. We have talked about all this in detail, about the wire length, about the number of buffers that are placed in the path. We have talked about all of them in a separate section, in a separate course of clock tree synthesis. And the next step, after we have done with the clock tree synthesis, there is one more step that we need to do, is the clock net shielding. Because clock nets are the most critical nets, and they have to be shielded. They have to be protected from the outside world. Okay, so what we'll do is we'll talk a bit about clock net shielding in the next video, since I'm already running out of time. So let's try to talk more about clock net shielding in the next video. Thank you.